Yeah, let me check. Okay, share the screen. Okay, start to record. Hey guys, so last night I purged the 10 project number 2 to the line group, so you might want to get started. So all the description is quite descriptive. Yeah, which very descriptive, so might get into the detail as soon as possible since yeah, it's going to take a while to figure out how why can you first of all you need to figure out why it is true and then figure out the reason, then you're able to code into a mathematics and figure out how the equation can be formed. Then you can put in the code and testing. So finally, I also need a user interface. I need a user interface like the first one I mentioned. Yeah, hold on. So I get a phone. Wait. Wait. Hello. So yeah, then so I try to figure out why and then today I gonna finish up the chapter 5, then chapter maybe I will next week going to move to chapter 7 or chapter 6. I'm not quite sure. I will decide later. Then the 2 weeks later going to present your final work. Yeah. So only 2 or 3. You only 2 weeks for preparation of your final or your the 10 project. Okay. So let's get started. 佩珍，我们上到第几页啊？讲义啊，佩珍，我们上次讲到第几页？
30几吧，30几。
怎么可能？
没有吗？
真的吗？
哦
真的讲完了。哎，General Solution，看一下这边讲完没 ？RMX， 这个不是讲完了？等一下，我看一下。哎，项羽，我们上次讲到第几页
41。
41。OK， 41。OK， so 41讲完了哈，项羽。
对。
Okay. So they're going to the first part of the minimum mean square control system. So this is okay. This is going to be the first part of the final 10 project, page number 1. So this is the xt equal to minus g over bf yt. So it's right here. Right here. Yep. This is the first part. You're going to implement your 10 project. 5.18. Equation 5.18. No, I get the tea. So get some drink. I'm sorry. So I'll be back in a minute. Okay, so I'm back. Okay, so we're going to move to the 5.1.1. It's right here. So it's this. We'll talk about the so it's a control block diagram of the minimum mean square error controller applied to the general Box-Jenkins function. So actually, it is a closed loop, and the output will be stationary, but it will not be uncorrelated in general. So this is yt equal to the b is a transfer function, a is AR, and the C is a moving average. So the epsilon come into the disturbance model C over A to produce NT. And the Bagoshy operator, this is a K-system delay, come into the transfer function polynomial B over A to produce signal. So in here, summation, in here, summation, the summation of the disturbance and the transfer function to produce Y right here. The Y is the output, and you might want to construct an SPC chart on the output on the output YT as well. So you can do that for sure. This is called not online SPC, is like the open loop SPC. Open loop. So you can do that. This is also a good, very good research work if you really want to work on. And then feedback YT. So feedback YT, this is the controller. Yeah, look at that. What is the controller? Minus B, minus G over BF, minus G over BF times YT. Let me say it again, minus G over BF times YT. Minus G over BF times YT, feedback then to produce the XT, right? You have XT then. Once I have an XT and which is fed back into the transfer function. There's a system delay K right here. Then doing over again. Get it? So this is the flow and the sequence how the minimum mean square error controller works. Question? Any question? 陈宇，这就是第一部分 Term Project Number 2。陈宇说话，听得懂吗？好 ，OK， Jun, can you figure it out? Can you understand what I'm talking about, Jun?
Yeah.
Okay,
Yeah.
cool. John,
可以，
确定
我
？OK，
再
上好，
研究一下。
上好。
OK，可以。
项羽，你才跟得上吗
OK，
？OK， 佩珍
可以。
，OK， 各位。
可以。
Okay, then go back to here. So move to the general solution to the minimum mean square error controller. So this is a conceptual model. So I mentioned only the conceptual model. Now we turn into the mathematical model. See that right here. Right here. We're going to talk about, yeah, right here. So going to have idea control. Okay, later, okay. So going to address a bit later. Since YT is observation and tail is a forecast error, this is a forecast where the control arrow with a tail on the top is a control arrow will follow a moving average. That's a F model when the control arrow like this. This is a F times epsilon t plus k. So this is the control arrow going to follow IMA of the order k minus 1. The order k minus 1. We mentioned last week. We mentioned it several times. So this is 1, always 1, times f1, epsilon t minus 1, up to epsilon t minus 2, until fk minus 1, epsilon t minus k minus 1. So factor out the backwards operator, k. Right? So when we factor out the backwards operator, now this forward operator, Q is a forward operator. So this is the moving average of the k minus 1. This is like we right here. Here. Right? Yeah, I think, yeah, not here. So we're already done. We're already done. So so try to minimize. Try to minimize the mean square error yt plus k squared. This is a variance of sigma epsilon 1 plus f1 square, f2 square until the fk minus 1 square. So the y hat is a forecast like this one. The g y, this is true. So the y hat yeah, let me show you why it is true. Xt and y. Y hat is this. Let this equal to 0. To let this equal to 0. Right? So y hat equal to move this part to the left hand side. This is minus the minus bf over g times xt. Based upon this, this is yt plus k hat. like this. Okay. Then from the above, the control rule can be stated as follows. Xt should be chosen such that the minimum mean square error prediction of the output over the system delay k equal to the desired output equal to 0. So going to testing the minimum variance control. There's several example we're going to so going to comparison with the ideal controller. So going to illustration. Go and test that. If a system is operating under minimum variance control, the output yt equals the control arrow follows and moving average k-1 process. So we like to test for minimum variance controller. So we check whether autocorrelation yt cuts off after k-1. If this is true, you are done. If it is not true, so yeah, it hasn't arrived the minimum variance condition. Let me say it again. Once we have the output going to follow the moving average, then we test the autocorrelation of the output, and yt should cut off after the lag k-1. If this is true, then the controller working properly, then the output will follow a moving average. If this is true, you are done. If it is not, it got to be something wrong with your controller. For such a case, this is the strong evidence that we have a minimum variance controller. So further reduce the output variability, it can be tried in the following way. First one, the reduce inherent variability. So yeah, like this. Yeah, this is quite different philosophy. So you like to reduce this. So you're going to have a direct manipulation on the tool. So like I'm going to directly work on the the PID control. I'm sorry. That is an internal control, like IMC, inch. So that's called an internal model control, called IMC, by using the state. So by stasis model, which will not be addressing this lecturing, since is quite of electrical or chemical engineering discipline, so which will not be covered by the industrial engineer. So then reducing hearing variability is first on top priority if you really want to do so. And the sooner you can control the system, smaller variance is, and decrease the system delay k to reduce k. That means you need to work on the metrology system. Need to work on the metrology system to let the metrology system can catch up with the processing step. Otherwise, it will never be possible to provide the timely feedback for the control action. So then reduce the feed-forward control. That would be straightforward. So something that hasn't happened yet. So going to just throw the message to the. So you're going to project what is going to happen. So what is going to happen in the future? Typically going to use a fuzzy. Yeah, that was quite popular and widely accepted control philosophy in the world by using the feed forward, like your air condition or something like a MRT in Taipei City. So actually, do you know how the MRT stop? When you the MRT going to going into the terminal or the stop station, so use a feed forward. Try to stop the train by using the fuzzy control. So actually, these project what how much degree or how much or how fast or what is decreasing rate of the speed of the current train, but it's going to arrive at the particular position of the MRT train. So or Taiwan high speed rail also using the fuzzy control for feed forward likewise. Okay. So find another controller factor, use a multivariate controller. So in which case, this is multivariate. Yeah, it could be possible multivariate. I would like to use if it's a multivariate optimizing control. So going to cast the optimization. I'm sorry. Cast the control problem into a form of optimization. Optimization. Then so there's a problem. If the B's transfer function is an unstable polynomial, then like this. Let me show you B. Let me see that. How can I do that? Where did I shoot? Okay. Okay. Let me. I want to show you. There's a cancel out. Let me show you. Right here. Not here. Hold on. Yeah, hold on. I try to figure B. RMX. It gotta be a slide to show you why. Okay. Yeah, right here. The B. The B point we are going to have a effect on the behavior of the XT. Okay. So, okay, let me show you some illustration. Okay, okay. Okay, the input is unstable polynomial. If it is unstable, it is strictly inside the unit circle, then the input xt. Since the b is a denominator, will diverge. Since it is unstable, when you put so b minus g over b bf, since the b is in the denominator polynomial. So to make this very unstable, will diverge, even though the output remain on target. So it always happen because the closed loop equation cancel all the zero of the b polynomial like this. Yt equal to this one. Then this is a closed loop equation. Let me show you. Unstable. So diverge including so Yeah, let me say that like this. So how such a control process output is stable, but the process input is not the yeah a Bevo stable. So this is the bivariate input and bivariate output. So reason for this is that the closed loop equation cancel all the zero roots of the B polynomial, including the unstable ones, even though this is one, whereas the unstable zero not cancel. In the minimum mean square error controller from the closed loop equation like this one. So YT move this epsilon T. Yeah, this is C. So so based upon this, so this is a backward minus BF. So let me see that we're going to get YT and YT, and in terms of that, we move this into the left-hand side, factor out YT, and this is BFC. So this is a BFC right here. We turn the BFC on both sides, the BFC epsilon T, move this, and going to divide by the ABF plus the BG Bagauge operator. However, there's a problem, the YT, the closed loop, and B will cancel out. Look at this, the B. Also in the numerator and the denominator cancel out regardless of the location is zero or zero root. So yeah, so it won't matter it is stable or not, it will be canceled out. So the YT going to blow out. So it is called this is wind up effect. Wind up effect. Wind up. In contour theory. Contour theory. So yeah, let me show you like this. So where is the thing? The B will cancel regardless of the location of its zero. So this unstable zero is not observed in the output, even though it is a zero. So but it will be observed in the output since it appears in the denominator of that equation. This is the problem. So well, even xt stable, YT going to blow out. So like this, this process, even though control process, the output is stable, but the process not both the bivariate input, bivariate output. So let me show you, yeah, like this, the BB going to cancel out. So example 5.4, Box and Jenkins zero order transfer function with IMA, like this. Yeah, there's an example. So gonna skip that PID later. No, it gotta be example. No, do we have it? No, not here. Okay, like this. Okay, 5.4. Box and Jenkins zero order transfer function with IMA noise, like this. This is RSB. B is a 1 right here. Xt minus K. K is equal to 1. And so this is RSB is equal to 1. So the other O is 0 for the transfer function for sure. Then generic form. So going to put this into this AYT plus a big times X T minus K plus C epsilon T. So A polynomial going to be 1 minus Q Bagauge operator. The B polynomial going to be the G. G times the backwash operator, 1 minus backwash operator, C going to be the IMA, the 1 minus theta backwash operator. This is A, B, C. The N going to, we take the maxima of the NA, NB, and NC. A is 1. B polynomial is 1, C is 1, so maxima is 1, NC equal 1 for sure. For both, F and G are zero order of polynomial. Things are 1. This K, the K minus 1 is 0, N minus 1 is 0 as well. So F going to be order 0, G is order 0. So this is Diophantine equation. Diophantine. We have, okay, the C right here. 1 minus theta backwash operator right here equal to the A. A is right here, 1 backwash operator. F is a 0 order, so this is a 1. So yeah, let's recap. What is F? F is like this, 1 plus F1 plus F2. So 0 order, so we only have the leading term. This is equal to 1 for sure. Get it? Okay, F1. Okay. We have 1 and okay, right. This is 1 plus the Q, the K equal to 1, the backwash operator minus 1. G is right here, G no. So this is N, this is N equal to 1. So this is 0, G no, right here. So we just just expand this equation. So multiply it out. This we just collect all the terms together. So this constant term in terms of the backwash operator as an unknown. So treat the backward shift operator as an unknown. Okay, then we have it. So we get, we're going to get this one. So minus theta, theta equal to the 1 minus G, right? So G equal to the 1 minus theta, right? So in such a case, so minimum variance controller minus G over BF times YT minus G. G is 1 minus theta. How can I get that? G is right here. G is right here. G no. G 1 minus G equal to the theta, and the G is moved to the left hand side. G is equal to the 1 minus theta, right? Equating the power like in the backwash operator to find what is the coefficient it should be. Then B, this is minus G, and B polynomial. Hold on, let me see that. No, it is B, and what is the B? Backwash operator. What is the B? B is this one, G, 1 backwash operator. This is the B. F is 1, right? Okay. F is 1. So we get this 1 minus theta G, and backward 1 minus backwash operator just spin into the summation of the Yj. So this is a summation. This is like a, yeah, let me show you. This is like a the 1 plus x and the plus x. and blah, blah, blah. And until that is equal to 1 over 1 minus x. The infinite series. This is like a Maclaurin series, right? So I mentioned this several times in the class. So just this turn into the summation of the yt. So it is in the this I controller in the PID. I controller in PID. I controller, and then for the implementation purpose, how can we get that? For implement XD, we going to let okay, IT into XD equal to this one. We move the backward operator, 1 minus backward operator to the left hand side. XD times the 1 minus backward operator equal to the 1 minus parenthesis 1 minus theta over GYT. So, and then this becomes XT minus XT minus 1, and XT minus XT1, the XT minus 1 move to the right hand side equal to the minus 1 minus theta G and the YT. Okay, so how can we get the 1 minus theta? Right here. Right here, 1 minus theta. So this is epsilon T IMA. This is from the disturbance, right? This is disturbance by using the ARIMA model. So the parameter theta is the parameter, and the disturbance model. Then hold on. Yeah, let me. Yeah, keep going. Hold on. Finally, YT. So once you get the previous control set up, the G, where can it get a G? G is a genome. Where is the genome? G is 1 minus theta. Theta is constant, for sure. Once you get a G and you get YT, then this is you get the recursion of the control. So then you get the recursion. Yeah, quite straightforward. Okay, this first example, like, yep. So the impermanent controller turned into the form, and the Joule and Soderstrom formulas can be applied in this example too. In this case, we have, yeah, something like that into that backward operator. Okay, so so yeah, it's a very this is particular interesting, the presence of the unit root in the denominator right here, or the integrator of the control rule imply XT will follow a non-stationary process of the adjustment like this. When we move this, the backward operator, and this, we move this to that, they're going to be the Nabra XT will be stationary. So how can we get XT? Once I get the difference data of XT, the XT turn into a stationary series. This could be too expensive in some process. Yeah, this is too fluctuating, too difficult to control. So it is not so realistic. Things are XT T minus 1 is a new called X prime. X prime is stationary. Well, yes, the way too expensive in practice. Why? Yeah, I changed the XT input, the tweaking the input variable too much from run to run. Yeah, this is way too much sometimes. So it will not be so realistic in practice. Okay, then. Okay, next example, 5.6, 1 minute. Hold on, 1 point. Is this one? Yeah, let me, my G, is this one? No, 5.6. I skipped this. 5.6x. Okay, I'm going to talk about this. Okay, 1 minute. Give you 1 minute to look through everything. Now 2 minutes. 2 minutes. I'm going to talk about this. Okay, just read example 5.6 now. I'll be back in 2 minutes. Okay, then. Okay, I'm back. So we're going to talk about the example 5.6. Yeah, look at this. We first of all, we look at the RSB. R is 1, the A polynomial S. S is equal to the 0. Yeah, let me see that. RS. And the RSK, K is equal to 2. So this A polynomial, this time that the 1 plus A backwash operator, B polynomial, BXT is equal to 1. C is 1 plus C backwash operator. So this is RSB. So let me recap. So what RSB is going to be the chapter. In the chapter 4, it should be in the chapter 4 RSB. Yeah, let me see that. Yeah, let me see. This is somewhere in there. Okay, I cannot find that now. However, just look my course slide. So okay, so I need to return here. This is chapter 4, chapter 5. No. Okay, return to here. So then since R is a polynomial, S is since only one term, this is only one term, so this is 0. So typically going to be the B known plus the B1 plus the B2, so the order is 0. And K is equal to 2 since X minus T. So minimum N, A, N, B, and C. A is 1, B is the max B is 0, C is 1, so max is equal to 1. So use a Diophantine. C equal to AF backward operator minus KG, and based upon that. So we just plug in those information A, B, C into here. So we just equating both sides. So 1 plus C backward operator equal to the A F. Since the F is a K minus 1, so K is equal to 2. So the F4 polynomial going to be 1 plus F1 backward operator, and G is a polynomial of order n minus 1, n is 1, so order n minus 1 is equal to 0. So this is G known. So left hand side is a 1 plus C backward operator and A, F, and backward operator K and G. Then we equate both sides. Equating both sides yield the following equation. So we're going to just rearrange in terms of the backward operator minus 1, backward operator minus 2. So equating both sides, 1, 1 equal. So C going to be equal to the F1 plus A. So there's a no, on the right hand side, there's the backward operator minus 2. On the left hand side, there's a no. So AF1 plus G no got to be equal to 0. So in terms of the power like backward operator minus 1, so say C got to be equal to the F1 plus A. So F1 equal to the C minus A. So those can be obtained from the original. Once while the disturbance model is fitted by using the ARIMA, CNA are known for sure. Then we would like to get that the A F1 plus G known must be equal to 0. This has got to be equal to 0, equating on the left hand side. So G known equal to the minus A F1. Minus A is constant, F1 is C minus A from the first equation. So the G known equal to that. Okay, then thus by using the minimum variance controller, xt minus minus G over BF, YT minus G, where is the G? G is right here. Right here, minus G known is A parenthesis C minus 1 over BF. BF, what is a B? B is 1. F is 1 plus F1 backwash operator. So 1 plus 1 backwash operator, F1 is a C minus A, so 1 plus C minus A backwash operator YT. So this is our minimum variance controller, right? Bingo. Perfect. Okay, then we got a 10 minutes break. So going to return after the break. See you later. Okay, I'm back. Okay, any questions so far? I think this is quite. I understand it's a little bit confusing, perplexing. Question? No? Okay, move forward. Another example, G minus theta. Oh, another example. Let me see that. One minus z over theta. Okay. Yeah, let me see what is this example. G1 minus theta. 1 minus theta, 1 minus 5. No, not this one. T 2 minus 2. No, G x e minus 1. Not this one. Okay, let's look at this. This is previous example, and this is deviation from target of system with an MMSE controller applied to an transfer function with unstable B polynomial. So yeah, this should be the target YT. However, XT going to blow out. So it's like this. This is the B. This is a previous example, 5.6. Unstable 5.7. Okay, let me just go through this. The unstable B polynomial MMSE finally turned into that by using the same procedure we have today. And so we have done this. So this, okay. A C minus A plus a C minus A YT, so we have done that. So this is another example. Then it's easy to see that the denominator right here, has a 0, the root at the back-Cauchy operator. This is equal to the -9. This is less than 1. It is within the back unit circle. So thus x will diverge. So from the figure 5.8, 5.9 illustrate this situation when the epsilon t follow a standard normal distribution. So x know that extremely large oscillation in xt, even though yt can be controlled, and the xt going to be divergent. So in practice, controller factor will heat bounds that the process must be obeyed. So that's just construct the xt, construct the SPC. In practice, we need to construct SPC on, okay, xt. In practice, we need to construct SPC on xt. So from that point on, the output will show non-stationary behavior. So this is figure 5.8 and 5.9. 5.8, yeah, 5.8 is this. Deviation behavior, this is quite stable. XT. Originally quite stable, finally it diverged xt like this. The value of the controller factor for process with unstable back the B polynomial is a transfer function. So MMS controller applied. So going to divergent right here. This is right here, divergent. So you need to take this. Excuse me, I just turn it off. Hold on. I need to turn it off. So when the xt time goes on, this is going the xt going to diverge. Okay. So the very large oscillation in xt in practice, a controllable factor will hit a bound. There must be a way, like for example, the xt must be lower bound, and the xt the less than the upper bound. UPPERBOUND like this to follow that. If either can follow that, and then even though if this is the case, we apply them. From that point, the YT will show non-stationary. Not like this. No, this is kind of beauty always in control. So the YT will not behave like this. Okay, then. Okay, look at this example. Then R is 1. S is only the 1. This is Debbie controller, so S equal to 0. Backward K is equal to 1. Then A polynomial is 1 minus theta backward operator, and B polynomial is G. C polynomial is 1 minus theta backward operator, and the maxima of the NA, NB, and NC is 1, and F is 1. Y, this is K minus 1. K is equal to 1. K minus 1 is 0. So this is 1. The N is 1. So the G polynomial is a genome, since this is order 0. So going to equate the Diophantine like this. Diophantine. C equal to AF and the backward operator minus KG. C equal to AF plus G. C equal to AF. And C right here equal to the AF plus the backward operator G. So just equating both sides in in power-like manner. So finally we find out, yeah. 1 minus theta backward operator equal to the 1 minus, we make some arrangement. So 1 minus the 5 minus genome. And yeah, this is 1, and this is minus the 5 minus genome. So in this case, the theta must be equal to the 5 minus genome. So genome equal to the 5 minus theta. And 5 and theta can be obtained from here. From here, right? So then the genome equal to the 5 minus theta minimum variance controller, and it's a minus G. G is genome, B is 1. B is a G. G, F is a 1. So this is minus G known over G YT. And G known equal to phi minus theta. So this is a minimum variance controller. Okay, then we move on to this. We try to solve. We try to solve this problem, the windup. Yeah, let me show you the process windup. Let me. Yeah, can I? No, why not effect? Why not effect? Effect in control system. Yeah, let me see if I. Anti why not integral? Why not in control prevention? Yeah, like this. No, it doesn't show. Okay. Anti why you did here. Let me show. Do you have a why not effect? No, it doesn't show any particular. It's always related to the PID control. It doesn't show. No. Okay, later, if I find. However, in the control theory, there's a called the process windup. Okay, then we have done this. Okay. Okay, this is this example. So this is yeah. Let me just go through this. The generalized minimum variance controller. So the large variability uncontrollable factor must be undergo when the manipulate under minimum variance control may not always be practical and feasible. So that's a question. So try to rectify this drawback. Then furthermore, non-minimum phase process such as the one encountered in this example 5.7, we cannot regulate impacts applied in that, since some other rule must be obeyed. So illustrate some of this idea like this. So from figure 5.10, yeah, like this. This is output using the open loop MBR opposed to B and minimum variance controllers A and B. And CND, minimum variance control, this is MMSE controller. So when we just controls, you can see that, do that, and then the fluctuation is greater than the open loop. So it is kind of the sarcastic issue. So let me see that. So it is based upon the x theta minus g over theta minus phi over g. Xt is theta minus phi over g. So it is this equation. No, this example. Using. Okay, this example. Then the controller for the case, the theta equal 0.5, phi equal to 0.5 autocorrelation. Theta is this is a moving average. It's a minus theta g equal to 1. If the epsilon t is the arrow follow the uniform distribution, 1 and minus 1. And the expected value of the epsilon t equal to 0. In such a case, the open loop simulation was carried out with the input vary at the xt between the -5 and +5 and -5 to let it go between this bound like this. It is this one. So this is the other control philosophy. So even though it's an open loop, but carried out with the input varying between this bound. In the second simulation, the closed loop by minimum mean square error performance achieved by this. xt equal to, g is equal to 1, theta -5, theta -5, minus 0.4 minus 5 minus the 0.9, the 0.9 yt. As can be seen, compared to the open loop, an MMSE controller transfer the variability from the output to the input. Transfer the variability from the response to the input, the control factor, like this. Like this. This is open loop, right? Open loop. And C and D. Let me see that using the open as opposed to the C and D. A is Y sequence, B is output for the Y noise, C is a minimum mean square control input, C is this, and D is a minimum variance controller. So you can see that like this. So to transfer the variability. So the variability from the output into the input variable. So so we might think of, this is the minimum variance controller. Sometimes if you don't just add additional constraint, even though you add something to that, it will not be the optimal as well. So for the A and B opposed to the minimum variance controller, this is input and output, the A and B. So this is a variability transfer into the input variable, even though the output, like this one, we would like to achieve that. So the variability transfer to the input. The variability is subject to a larger fluctuation. However, the input going to have a smaller variability on xt. So which one is better? We need to get a trade-off between that. We want to have a smaller variability on the YT. We need to suffer from having the larger variability. How about the open loop? Might be a greater. So this is totally tolerable. Then we have a better or less variability on xt. So we need to have a trade-off. The YT. Okay. Yeah, this is a quite intriguing question to be asked. Then, okay, move to 5.3. 5.3. Right, generalize the minimum variance controller. The previous ones is general, so we talk about the generalized. We add the Lagrange multiplier at so going to have a constraint on xt, a price, a constraint input on the input. Then so called the generalized minimum variance controller as compared to general. So this is a generalized versus different. The general going to be the first part. So generalized minimum MMSE control is the part of the. It's the second part of the term So this is natural expansion, minimum variance control. Okay, you look at this first. I will be back in 1 minute. I will be right back. Okay, I'm back. So we're going to put the constraint on the input, like in machine learning, we put the regularization. So yeah. First of all, in machine learning, EARN, machine learning. In machine learning, we always like to minimize the loss function. So totally the loss function is equal to the MSE to minimize the mean square error and the plus the LAMBDA 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 plus the regularization to avoid the effect. So that's why in the machine learning using the same quite similar rule in order to avoid overfitting, put a lambda of that, like in the logistic regression or in the yeah, let me see that, or SVN regression. We'll put a lambda over there and the SVN support vector machine like that. We'll put the lambda of them, call the regularization. Yeah, let me show you. Regularization. Question. Regularization. Yeah, I would like to L1 and L2. Do we have a question? Yeah, like this. Approach adding a regularization like this. So like this, or no, I would like to have a better illustration. Hope I can have a better call. No. Yeah, like this. Yep. Yeah, it's cost minimum, the regularized estimated. So we're going to put that. This is L2. L2, this is the norm in L2. The L2 norm. This is L2. This is L2 norm. And so put the summation, this is the loss function. This is the loss function, try to minimize the error and lambda over to the, so try to W, this one, this is W2, the W, and this is W1, W2. This is, you try to minimize that. So intuitively, we can think of the sphere at the coordinate center in the figure above as our budget. So objective is still the same. So we want to minimize the cost function. This is minimize the cost function. So this is the first. I'm sorry. This is the first one. We'd like to minimize cofine. Why we need to add that? So why? Since this is regularization, we want to avoid overfitting. So however, we not constrain regularization term, we want to get as close as possible to the global minima. Global minima is this. However, we don't want to spend it too much. So as our budget, our objective is still the same. We are now constrained by regularization term. We want to add closer to the global. Why? Staying within our budget like this. Staying our budget as close. So or this is L. This is L2. The other is going to be in the square. This L1, like put this. Yeah, let me put that. This is value of this is called of x w1 absolute value. Let me see that the sum. I would like to see the sum. The sum of the ABS absolutely of the one plus ABS the W2. So this is L1. This is L1. This is L1. This regularization process. Okay, like this. Yeah, I think it's a good illustration. Let me see that. Do we have a no? Do we have a yeah like this? This L2 for sure. This R is regularization R multiplied the Lagrange multiplier. The lambda called the Lagrange multiplier, and yeah, I think no. I would like to see the graph. I would like to see the graph. Okay, this one. Okay, this is sigmoid. Okay, this is underfitting. So like this. So this is perfect. Yeah, this is perfect. So we misclassify the instant right here, and this is a underfitting, so it doesn't fit that well. This is a perfect fit. However, sometimes it is overfitting like this. Yeah, it's overfitting. The high variances, too much variances. So we're going to reduce the variances. That means we just control and set a boundary on the W1 and W2, so this is overfitting. So this is why we put the regularization. This is nothing. This is the something we don't want to see. Okay. Then back to here. So put the constraint right here. Lambda can be interpreted as a Lagrangian multiplier of the following constraint. The xt squared, just put a boundary in the xt equals to 0 is used to dictate or denote the current operating conditions, which correspond to the constraint on the variance of the input. Then in order to minimize J1, recall that and this is a prediction error. The prediction error follow a moving average sequence which contain the epsilon t plus k minus 1 until the t plus 1 are all uncorrelated with y t plus k given t. So we like to do this. YT squared. We minimize J1. YT squared plus lambda xt squared. And lambda, the YT is equal to y hat plus y tail squared. The y hat squared plus the 2yt hat, y tail, plus the y tail squared plus the lambda xt squared. So which can be separated in two terms. So first one, this is the forecast error, and this is the estimate plus the Lagrange multiplier. This is penalty term. In the NLP, we call the penalty. It's called the penalty time. Which does not depend on xt. The forecast error. So minimize J1 is to minimize J2. So try to minimize this. There's nothing to do with the xt. This following the IMA. No, the moving average of the k-1. So to minimize J1 it is equivalent to minimize J2. Is yt plus k given t hat squared plus a lambda xt. So this is a random variable. So take the integral from the negative infinity to infinity dxt. Since xt is a random variable. So which or what level of xt should be set to have a better performance? Yeah, this is a question. We ask the question. So that's why this is take the expected value. We should take the integral of over its a PDF. The probability density function. Then instead we can minimize that. Yeah, for sure, given the yt minus 1. Yeah, based upon the previous observation, so that is equivalent or can be written as a Rmax form. So in its MMSE forecast equal to the A plus the B xt minus k plus the c and the hat y hat expected value of the yt plus k can be written as a g over c yt bfc xt. So this is in the Rmax we mentioned previously. So based upon this xt, we have this one. So the J3 GC plus the B over XT. Since this is error, this is a forecast equal to that, and the forecast can be written that this y hat squared is equal to this square plus the lambda xt. This is called lambda xt squared. So which can be minimized. We take the partial derivative. Taking the partial derivative with respect to the unknowns. So this is the partial J3 with respect to partial XT. XT partial, this one is equal, nothing to do with this one. So this is a BFC, gotta be the initial condition, B0. So this is the initial condition. This is yt plus k given t squared. Therefore, the partial derivative with dxt equal to 0. So this is the initial condition. The BFC put the 0 into that equal to the initial condition of the transfer function in B. Take the xt equal to 0, the 2b0 and gcyt bf over cxt and the 2 lambda xt equal to 0 and soft xt equal to 0. How can we get that? Finally, from which we just collect all the xt, move to the xt right here. This is we have a xt less than equal to 0, and 2 cancel out the b0. So collect all the xt and move the other side to the left-hand side, right-hand side. Finally, we get that xt equal to the minus g over bf plus lambda over b known g. As long as lambda equal to 0, x equal to 0, then there's a xt equal to the minus g over bfyt. This is reduced to original one. So when lambda approaching 0, it approaches minimum variance controller. Approach the general minimum controller. If the lambda approaches infinity, yeah, this is really big in the denominator. Xt approach to 0, so you approach the open loop. The open loop is SBC. SBC is a no control. No control. So this is the second part. Yeah, let me see that if I put everything correctly in. Let me see that. Time series. Let me see that. Yeah, I hope I get it right. Yeah, this is A and B and C are ABC polynomial, order less than or equal to 3. Yeah, this is prescription. Know that the delay equal to 1, k equal to 1. And also know A and C start with a 1, and C start with a 1. And the B does not start with 1, B start with a B node. The epsilon should follow an ID. The normally independent distributed random variable simulate 500 YT. As a typical controller, your random program should be simulate any given controller. And also extra credit, you're going to put the lambda version to generate or simulate a generalized minimum variance controller. Okay, I think this is quite straightforward. Yep. Okay, so this is going to be the second part of the project number 2. Okay, let me take an example. Example 5.8. Example 5.8. So this going to be our second part. Equation 5.19. The second part in the project 2. This refer to the equation 5.19. Okay, I give you 2 minutes. This example 5.8. We're going to talk about this. Okay. Okay, 2 minutes. Now, everybody read that, 5.8. Okay, I'm back. Five point eight. Okay. This is another transfer function example. Boxon Jenkins transfer RSB plus IMA. R is this one, 1. There's only one term, 0, and K is equal to 1, K equal to 1. Plus this IMA, this is integrated ones. This is moving average. So we put everything to the left-hand side, multiply 1 minus delta backwash operator times 1 minus backwash operator on both sides. So we get this yt equal to the g times the backwash operator xt minus 1 plus the 1 minus delta backwash operator 1 minus delta backwash operator epsilon t, equating both sides. Then take the collector term in terms of the backwash operator minus 1, backwash operator minus 2 on both sides. So then from the diaphanting, C equal to the AF plus the Q backwash operator, backwash operator minus KG. Then the C is equal to that. C is this one, equal to the AF. A is this one. And the F is K minus 1. This is K is 1. So this is 1. AF plus G is NA, MB, and C. And A is equal to, I'm sorry, A, B, C. B is maxima. This is 2. This is 2. So actually, the N is a maxima, NA, MB, and C. So it's got to be equal to 2. So N equal to 2. 2 minus 1 is 1. So this is G is this is a polynomial of the order n minus 1, and it's equal to the maxima of the NA, MB, and C. So that is so the n is equal to 2. 2 minus 1 is 1. So the G polynomial gotta be a polynomial of the order 1. G known plus the G1 backwash operator, equating both sides. So in terms of the in power like, the backwash operator minus 1, yeah, equal to that, minus delta, yeah, this is right here, minus delta, minus theta, where is that gotta be, yeah, minus theta minus delta gotta be minus delta minus 1 plus the genome. So after we're going to cancel out this. So genome gotta be equal to the 1 minus theta for sure. Okay. Then power like in terms of the backwash operator minus 2. In here, the theta delta equal to the delta and plus the, yeah, there's the power like in minus 2, the G1. So G1 equal to the theta delta minus delta. Factor out delta is the theta minus 1. Okay, cool. Then finally, we just cast it into the XT. So this is the generalized minimum variance controller. Where is that? Right here. Minus G over BF lambda B known C YT. So we got that. This is minus GBF lambda over B known C. So G is equal to genome plus G1. Genome is a 1 minus theta. G1 is the delta theta 1 backwash operator. Okay, no problem. The B equal to right here. G 1 minus backwash operator. G1 and backwash operator lambda over the B known. B known is the, okay, hold on. Lambda over B known is G. Initial condition. B known is a, yeah, G. B known is a G. This is the initial condition of the B polynomial in transfer function, G. And C polynomial is equal to that. 1 minus delta backwash operator, 1 minus theta backwash operator, 1 minus delta, 1 minus theta, 1 minus theta, 1 minus delta. Okay, 1T. So this going to be our generalized minimum variance controller for what? For this one, example 5.8. 5.8, like that. This is a clock, a very famous example. Clock Gaudreau controller, which is a single input, single output, called the Cisco system. You see? Single input and the single, I'm sorry, output system, known as the Cisco system. Okay, we have a break. Catch you later in 10 minutes. See you later. Okay, we're back to class. So all we finished chapter 5. So fanting. So finally we have this one, and so let me take another example. Another example 5.9. 5.9 is right here. This is 5.8. 1 minus 0.7, 1 minus should be another example. Okay, like this. Clock a Gauss-Ropp controller, unstable B polynomial. Consider the case considered earlier when the B polynomial unstable. The B polynomial in here. It's just a minus 0.9. It's a less than 1. So yeah, going to generate the unstable xt. So minimum variance controller minus G over BF, minus G over BF. YT on target, XT still blows up. Why? Let me see, like this. This is in here. Okay. The minus 1, this is minus 1 minus 0.7 backwash operator 0.9 plus backwash operator YT, XT on target, YT on target, XT blows up. There's a illustration like this. This one. Then to make the oscillation, make the YT on target, however, XT blows up after 166 period. In order to rectify this difficulty, or we call the window wind up equation, we're going to add the penalty. This is Lagrange multiplier in here. So the effect of the increasing the lambda as a difficulty form depicted in the figure 5.11. 5.11. Where is the 5.11? Yeah, 5.11. Okay, for lambda, when we increase the lambda, so we're going to sacrifice the variability of the YT, and the XT going to be reduced since we impose the constraint on XT. We impose constraint. So and like so there's a compromise. So we like to, when lambda equal to 0, that means this is reduced to the general minimum variance control. So this is minimum variance control. However, when we increase the lambda, when lambda goes to infinity, this is open loop. When lambda is equal to infinity, it's an open loop. Then we just reduce the y. When there's a so variability. So this is a lambda. What the variance of the xt, it is quite big, and reduce the variance of the xt. So this is a compromise between the xt and yt. This is a hyperbolic functionality. Hyperbolic functionality. Relationship between the variance E and self YT between them. So yeah, this is typical behavior. This one, as lambda increases, when lambda increases, large reduction in xt obtained for only small increment in the YT. Yeah, this is yes, just lambda, just increase a little bit, just only sacrifice the YT a little bit, especially in here. So this is the region we want to explore, the region. So we want to explore the region of lambda to compromise. Yeah, this is our objective. Then, yeah. Then this is another example. This is 0.9117. Okay, then this is another example. The minimum variance is xt equal to that, YT on target, xt still blow out. Then we add the lambda, so A, B, C, G, and F. Then, so finally just cast into that minimum variance controller. So you want to take a look at this part. This is simulation. Finally, you are able to, so this simulated behavior of the input and the output when using the Clark-Gauss-Rock generalized minimum variance controller when lambda equal to 0.3, when the error following the standard normal distribution of example 5.9. Then using the different lambda penalty factor or penalty discount factor between the relationship of the variability of the YT and XT. So when lambda equal to 0, this is general minimum variance controller. XT diverges. We put a quite minor penalty on the XT. So while greatly reduce on XT. So increasing, then we increasing the YT sacrifice. No, we just to put the more bounds or put more constraint on XT, smaller XT, going to transcend the larger variability on the YT. I think that will be quite fair. Get the smaller variability of the XT, transcend the variability into the YT. So then I think I'm done with this example. The figure just constraint. No, I just, okay. Let me see that. Setup adjustment problem graphs. Okay, harmonic rule. Oh well. Oh, I'm gonna skip that. No, I'm gonna skip that. I don't want to use that. Okay, they're going to be the end of the chapter 5. Chapter 5. Okay, so you need to get into the detail. How can you prepare your the term project number 2? The next one, I could directly move to the, let me see. Yeah, hold on, give me a minute. Give me a minute. chapter 4, chapter 5, chapter 7. Yeah, give me a minute. Give me a minute. I do the transformation into the from the PowerPoint to the PDF. Yeah, talk about this. Okay, I talk about this EWMA. Let me see. How can I? And culture version time series. Yeah, please download. Hold on. I'm going to purge it to the line group. Hold on. Yeah, got some problem. It got stuck. How come? No. How come? My computer is stuck. I don't know. No, I don't know how to do that. My computer is down. Can you hear me? Can you?
Yes.
Well, my computer is stuck. Geez, how can I fix that? I don't know. I don't know. I don't know. Let me just do that. Yeah. Okay, I'm back. Can you hear me?
Yes.
Okay. Yeah, so I need to just reload it. Hold on, give me a minute. I need to reload it. Time series, course material. finally, chapter 7. No, it doesn't work. No. Okay, I tried to put it on the line group so you can download it. Yeah, let me do that. Open your line. This is not this one. There you go. I put the chapter 7 in the line group. Can you see that? Guys, can you?
Yes.
Okay. Okay now, so just go with the chapter 7. We take a very quick look at chapter 7 since it related more industrial products and the industrial flavors. Okay. Okay, I'm gonna turn the line off since it's too noisy. So, chapter 7. Okay, this is time series analysis, chapter 7. No. Okay, then. This is EWMA feedback controller in and the run-to-run control problem. So run-to-run control system always very important question and very important research area in the semiconductor manufacturing. That's called the run-to-run control. It's called the run-to-run control. So in this case, we're going to talk about the CISO system. CISO system is single input and a single output system, particularly in the semiconductor. Manufacturing problem. So this typically it is a combination, a synergistic integration between the SPC and the EBC. So what is the purpose for each role in the run-to-run? Called synergistic integration. So typically SPC, this is for monitoring the input and the output. Typically, we might put a deadband, DEADBAND on ST. So deadband, that means within that range, we don't trigger, we don't manipulate the XTs in order to maintain the stability of the of the process from the perspective of the input variable and put SBC on YT. If we put an XBC on YT, that means we'd like to control the output variability. Oh, this is SBC. Then it contains two major parts. First one called the regression model. Why do we need that? Would you like to say why do we need a regression model? Somehow, to make a wild guess, why do we need a regression model? Somehow.
Hi.
What do you think?
Predict.
What? Why do we have a regression model? Make a wild guess. 为什么? Why?
Predict.
Predict. Oh yeah, that's good. Pei Zhen, what do we need to predict? Predict what?
Predict what? 很多哎，都
For
可以。
example, what do we predict?
天气、股价、房价。
Okay, sure. So going to predict. So actually, the regression is used to predict the unknown parameters in the model. Typically used for that purpose. Then in linear regression model, what do we predict? And in regression model, what? Is there any unknown parameters in the regression model? Yeah. For example, 来给我们例子吧。For example.
线性回归。
Linear regression model, what parameter need to be estimated? For example, give me an example.
Beta 1 和 Beta 2 之类的。
Okay, so we have a beta 0. It is intercept. Yeah, beta 0 intercept. This is also known as a process offset. And the beta 1 is this slope of the process variable x1. And or yeah, you can say that beta 1 is sorry. The 1 is the regression coefficient. Yeah, regression coefficient of the pure quadratic term. Like this, beta 1 like a beta. Beta times the x1 and square. Yeah, let me show. How can we show you the square? Hold on, the square. Okay, hold on. I want to show you the square. Shift like this. The beta 1 times the x1 squared. This is a second order model. No, the second order term. Okay, cool, very cool. So regression online process control is like here. feedback controller. Yeah, typically it is a feedback controller. Feedback controller. So this how far the feedback controller provided. It depends on the processing tool and the metrology tool. It depends on what is the system delay to be existing between the processing step and the metrology step. Yeah, typically we have a relationship need to be discussed. Then this noise output, so this online control estimation, that's a wide synergistic integration between SPC and APC. So this is basic structure of the run-to-run controller as applied semiconductor. Yeah, let me see. Yeah, I would like to show you what is the textbook say about this bar. Come on. Recursive estimation, I hope I can address this later in the next week. Yeah, there we go. There we go. Okay, chapter 7. Chapter 7, yeah, like this is equipment wafer flow to the metrology and quality characteristic of measurement. Now, typically I call this a measurement. Measurement data. And is fed back to the control mechanism. Control mechanism. Then run-to-run control provide the recipe setup. Yeah, so control that equipment controller. Yeah, so this is a basic structure. Run-to-run controller is applied in semiconductor manufacturing. Then further, the task of the EWMA controller is to update the value of the input variable at each run to compensate for the process changes without increasing the variability of the process output. So like this is a recipe into the linear model and the recipe, and then this is the set point into the process, the output going through the EWMA filter, and there's a target and the setup just placed right here for comparing the difference between the observed and the estimated or forecast or estimate of the process output. And back to the controller 1 over B. The B is a process gain. Process gain. Process gain feedback. The linear controller finally calculate the going to the update of the process offset. Then back to the process, going over and over again, iteration by iteration. So let me consider a single example, single EWMA controller. So in which case, let us assume that the input-output relation of a manufacturing process can be modeled by the following formula, in which case the YT denotes the deviation from target. And epsilon T, a base, a Y sequence is a white noise process. So it is a simple regression model where the parameter alpha is known as a process offset or intercept, or the beta is a slope of the process gain need to be estimated. That's why what kind of parameter need to be estimated by using how can we estimate then? For the estimation problem, so typically we're going to perform experiment. EOE. To get the data offline, this is excuse me. Experimental study to get the data, fit the model, and give the parameter estimate or use a response surface methodology, the RSM. Response surface method to get those parameters done. And the approximation to the true system to underlying transfer function. No, so equation 7.1 implies that there are no process dynamics, and that no process dynamics, since there's only one, this is called the DEPI control. Okay. So going to directly follow what is the output is a variable called the DEPI control. So exhibit no process, there's no process dynamics. The process dynamic and that effect of making change in the control factor is fully observed in the next measurement of the quality characteristic. So such responsive processes are common in discrete part manufacturing, called the DPM, discrete part manufacturing, known as DPM. Okay, the most of the industrial engineering deal with the cases that relate to a DPM. So if the process parameter are known, for example, the alpha and beta, the alpha and the beta are estimated through EOE, for example. They are known. Then a very simple minimum mean square error controller can will be equal to xt equal, so less than equal to t equal to 0, and xt equal to minus alpha over beta. So which is essentially a feed-forward controller of the type discussed in the example in the chapter 5, first example. Yeah, if we can do that, then in practice the parameters are unknown. So alpha and beta, if this is true, then we can do the feed forward. However, they are not true parameters. The best we can do is to provide the estimates for these two unknown parameters, or need to fix at a particular level for beta, since the beta cannot be changed from batch to batch, from run to run, or from wafer to wafer. So noise is sometimes it's not white. Of course, the noise typically is IMA. Yeah, sometimes I may. So, so common periodic semiconductor. Oh, geez, what is that? I don't know. So to estimate the gain of line using the design of experiment technique and feeding the linear regression model in the 7.1. And this provide the beta head equal to B, an estimate of the gain can provide an estimate of the intercept of alpha as well. This is a process offset. However, to protect against a model drift, this is a process drifting and other process dynamics. So EWMA control estimate the offset from run to run, like offset. YT minus BXT minus 1, YT minus BXT minus, move that second part to the left-hand side in order to provide the estimate from run to run, recursive estimate about the alpha. XT minus BXT minus 1, and then previous one YT minus 1 minus BXT minus 2. There's always this is K equal to 1. The system delay K equal to 1. Provide estimate of the alpha at each sampling point T. If the 10 point T, going to provide AT. At the time T minus 1, provide the estimate AT minus 1. So we can average this to compute a better estimate, or even better, we can use an exponentially weighted the scheme to give them more weight to the more recent observation, give the less weight to the more remote observation like this, the EWMA. So like this is previous estimate 1 minus lambda, and this is the put the more the weight on the previous estimate and put a complement discount factor lambda, the weight, this discounting factor lambda put, that is a weighting factor put on the current observation, YT minus B, XT minus 1, and so on and so forth. Like this one, like this one, like this one. So it's exponential weighted. Okay, I think I'm done with today. So I try to finish the chapter 7 next week, and remember to bring those. So you might want to starting to think of how you can proceed with the term project number 2. Okay, so I see you next week. Okay, thanks for your joining today's class. So always be prepared and read the book and look into the detail of my slide and start to work on your term project. See you next week. Okay, bye. And remember to put the YouTube link to me, provide by Payson. All right. So I see you next week. Bye.
Professor.
Yes, any question?
Yes, I want to make sure for the term project. So based on your description, so we can use the Excel?
Excel? No, I don't think so. No, I don't think so. No, I don't think so. You better program by Python or programming language. Okay. No Excel, please.
Okay.
Yeah.
Because on your description, using spreadsheet application, you develop simulation program.
Okay, this is my mistake. No Excel.
Oh, okay.
No Excel. The Excel, okay. Well, since Excel cannot provide you the dialog box, like it doesn't provide the interface.
Okay, thank you, Professor.
Except you can program it in, hold on, in Visual application. VBA can be can be a possible option. However, well, a purely Excel, no, it doesn't work. You need to program in VBA. So VBA is acceptable, or you can Python or C++, or or are acceptable. Is that clear to you, Jun?
Yes.
Okay, so any question for the term project or today's class? No?
No.
Okay, I see you next week. Okay, study hard. Okay. Don't go away too often. No, don't go out too often. Always stay home to reading the paper, reading the textbook, and doing your homework. Stay away from the trouble. Okay, I see you. Bye-bye.